Howdy! Welcome to Aspire Mountain Academy. I'm Professor Curtis, your instructor for this course in introductory statistics. In less than 10 minutes, this video provides additional practice in using the multiplication rule to perform calculations. Let's get started. Let's start with an example where we're doing some acceptance testing, and this is a common use of statistics in a manufacturing environment. So let's say we've got a manufacturer of steel rods. And what we're going to do is, before we deliver the lot of steel rods to the customer, we're going to take a sample from that lot and test it. And if the sample passes the test, then that entire group, which is the lot, is going to be shipped to the customer because it passed our test. So let's say we've got 1,500 steel rods in the lot. We're going to deliver it to our customer. And if we were to test each and every rod in the lot, we would find there are 276 defective rods in the lot. But we're only going to select 5 rods for testing because we don't want to actually test each rod in the lot. So under those conditions, what is the probability that the manufacturer will accept the entire lot? So the first thing we want to do is use our multiplication rule. The probability that all 5 are good is what we're looking for, because this is the probability that we'll accept the entire lot is the probability that all 5 of the rods we sample are going to pass our acceptance testing. So this is the probability that the first one checks out, and which means multiplication, the probability that the second one checks out, and the probability that the third one checks out, and the probability that the fourth one checks out, and the probability that the fifth one checks out. Sometimes I find it helpful if you just write out everything here, because then it helps you to know the different pieces you need to put together in order to calculate your probability. So now the next thing we're going to do is calculate each of these individual probabilities. So the probability that the first one checks out is 1224 over 1,500. Where does the 1224 come from? Well, it says there are 276 defective rods in the lot. That means there's 1,500 minus 276, which is 1224, and that 1224 represents the portion of the lot that is actually good, that checks out. So that's the part that's good. The whole is 1,500. So that's going to be there on the bottom of our fraction. So the part is the 1224, and the whole is going to be 1,500. Now, the probability the second one checks out is 1223 over 1,499. Why these numbers? Well, we took one rod out. We're selecting without replacement. That means we don't put it back in to be sampled again. So we have to adjust our numbers when calculating out our probability. There's one less good rod in the lot, and so the part and the whole are each going to decrease by 1. And we're going to see the same thing when we calculate the probability that the third one checks out, and the fourth one checks out, and the fifth one checks out. Notice with each of these numbers, the part and the whole each decrease by 1. That's because we're sampling without replacement. Now that we've got all of our individual probabilities, now we're ready to multiply them together and get our final answer. And when we punch that out on our calculator, we're going to get 36.4%. This is the probability that the manufacturer will accept the entire lot. 36% chance of accepting the lot is not all that great. So if I were a quality assurance person, quality engineer, what have you, I'd be looking at this number and saying, hey, we got to go back and look at our process, because this is just not good enough. You need a much higher probability that the lot's going to be accepted, or you're eventually going to run yourself out of business, because your customers won't want to buy from you because you keep delivering them defective rods. As you can see, that you start multiplying these things together, okay? So you can imagine that in certain situations, the calculations can be quite cumbersome, especially when you've got dependent events we're having to subtract 1 from the part and the whole for each successive part of the calculation. So when you're doing an independent calculation, it's no big deal because all the numbers are the same, and so you just raise that one probability to the power of however many of those probabilities you're trying to multiply together. When it's dependent, though, it's a very different scenario. So let's look at this case where we've got 3 that are being multiplied together. We can actually make some of these calculations more manageable if we treat the dependent events as though they're independent. And we can do this when we have a small sample drawn from a large population. And this is where the 5% rule that I mentioned in an earlier mini lecture comes into play. So in such cases, okay, it's rare to select the same item twice. And so because of this, if the sample size that you're taking out of the population is no more than 5% of the size of the population, then it's typically okay to treat the selections you're making as being independent, even though in reality they may be dependent. This rule of thumb applies, regardless. So, technically, it's not the right thing to do, but it makes the calculation a lot easier, and the result you get at the end is not that much different from the result you would get if you actually did keep treating everything out as being independent. How does the probability of accepting our lot of steel rod compare by assuming that the test events are independent? What if we made that assumption? I mean, we are sampling 5 out of 1,500, so we're well within that 5% threshold. So what happens if we recalculate this using this assumption? Well, the probability of the 1 is going to be 1224 over 1,500. There's 5 of them, so we raise it to the 5th power, and we get 0.362. Not appreciably different from what we saw previously. So it's going to compare well. So this is a rule of thumb to keep in mind that can help make some of your calculations a little bit easier. Let's try this out on an example. And of course, the example I'm going to choose is going to be chocolate. Duh. Management at a local chocolate candy factory commissioned a survey of 2867 consumers surveyed. 198 reported buying chocolate from this company within the past month. So if one of the survey participants is randomly selected, what's the probability this consumer did not purchase chocolate from the local company in the last month? So here we've got our calculation. We're going to take 2867 minus the 198 because we're looking for the probability that the customer did not purchase chocolate from the company. So we're given the 198 that the company did purchase the chocolate from the company. We have to subtract that out from the whole to get the part that represents the customers who didn't purchase chocolate from the local company. So that's going to be 2669 over the 2867, and that, which is the total, that's the whole, and so that gives us 93.1%. So if 15 of the survey participants are randomly selected without replacement, what is the probability that none of them purchased chocolate from the local company in the last month? Go ahead, stop the video here, see if you can tackle this on your own, and then we'll come back and explain, see how you did. Okay, let's see how you did with this. So these are dependent events. So if you want to multiply 15 fractions together, that's going to be pretty cumbersome. But if you recognize that 15 is less than 5% of the whole, which is 2867, you can just assume that they're independent. So then the calculation is going to run this way. You take the 0.931 that you calculated previously, raise it to the 15th power, because there's 15 participants. And that's an easy enough calculation to run. You get 0.342. And that's all there is to it. So this little rule of thumb comes in very handy when you're trying to calculate some of these probabilities. And that brings us to the end of this mini lecture. I hope you found it helpful. You can find more mini lectures for this and other courses at AspireMountainAcademy.com. Thanks for watching. I'll see you in the next video.